Hey, Harsh here. Today we're going to talk about HTTP, HTTPS, and WebSockets. Let's start with the very foundation. HTTP or Hypertext Transfer Protocol. Think of HTTP as the language that your browser speaks to the servers. It's the rule book that defines how they communicate. The model is simple, client and server. Your browser is the client and it opens a connection to the server, sends a request like give me your home page, waits for the server to respond, and then the connection closes. That's it. One request, one response. But here's the critical concept you need to understand. HTTP is stateless. It means that server has no memory. After it sends a response, it completely forgets you exist. You could visit the same website 5 seconds later and the server treats you as a complete stranger. Then you might ask, then how do websites remember my login? And that's a great question. That's where the concept of cookies and tokens come in. Those are layers we add on top of HTTP. The protocol itself is total amnesia. The statelessness is actually what made HTTP so scalable. No state to remember means no memory overhead per user. HTTP wasn't always as smart as it is today. HTTP 0.9 came out in 1991. Tim Berners-Lee invented it at CERN just to transfer HTML files. It was a dead simple only get method, no headers, no status codes. You asked for a file, you got raw HTML back. That's it. Then came HTTP 1.0 in 1996. This was a big upgrade and we finally got headers and status codes. But there's a problem. HTTP 1.0 opened a brand new TCP connection for every single request. Every image, every CSS file, every script, a new connection each time. Imagine you are on the phone with someone and after every single sentence, you hang up and dial them again. That's a lot of overhead. HTTP 1.1 came just a year later, and this is what we have used for over 20 years. And the major feature here was persistent connections, also called keep alive. Now you open one TCP connection and reuse it for multiple requests. One phone call and an entire conversation. This single change drastically reduced latency and made the modern web possible. So what actually travels across the wire when you make a request? First you have the start line. This contains three things. The method, like get or post, the URI, the path you are requesting, like /API/users, and the HTTP version. Next, you have the headers. These are the key value pairs that carry metadata. Think of it like an envelope of a letter. They tell you who it's from, what the type of content is inside, authentication tokens, and so on. Common headers include host, user agent, content type, and authorization. Finally, there's the body. This is optional and used only for post or put requests. It contains the actual data payload like JSON when you're trying to submit a form. In HTTP 1.x, it's all plain ASCII text and you can literally read it. If you open Wireshark or any other network debugger, you can see the actual words like get/index.html HTTP/1.1. It's human readable, which makes debugging a dream compared to binary protocols. What does server send back? The response starts with a status line consisting the protocol version and a status code, which is a magical 3-digit number. The status codes are grouped into 5 families, and once you learn them, you can debug almost any web issue. 2xx means success. 200 OK is your best friend and it means everything worked. 3xx means redirection. The resource moved and you need to follow a new URL. 4xx means that you messed up. 400 is bad request. That means your JSON is malformed. 401 is unauthorized. That means you forgot authentication. 404 means not found. The resource doesn't exist. 5xx means the server messed up. 500 is internal server error. That means something crashed on their end. The standardized system is what allows any client browser, mobile app, Python script, IoT device to instantly understand what happened without passing custom error messages. It's an elegant design that has lasted decades. Let's imagine a scenario. If you are in a coffee shop Wi-Fi and you log into your bank using HTTP, anyone on that network can read your password. Literally, just read it character by character because HTTP is sent in plain text. Enter HTTPS, HTTP secure. It's not a new protocol, it's HTTP wrapped in a TLS, Transport Layer Security Tunnel. Before any HTTP data is sent, a TLS handshake occurs to establish encrypted communication. Here's how it works. First step is client hello. Your browser says, hey, here are the encryption methods that I support. Then server sends an hello and a certificate. The server says that let's use this cipher and here's my certificate to prove that I am really who I am claiming to be. Then a key exchange happens. Your browser verifies the certificate against the trusted certificate authorities. Then both parties generate symmetric session keys. Encryption communication happens after this step, and now everything is encrypted. If someone intercepts the traffic, it's unreadable garbage to them. This is why you should never enter sensitive data on a site without the padlock icon. HTTPS is a non-negotiable. Google even penalizes HTTP sites in search rankings now. HTTP is unidirectional. The server can only speak when the client asks it to. It's like a waiter who only comes to your table when you yell, "Waiter." If the kitchen has a fire, they can't warn you unless you happen to call them over. Imagine you are in a chat room, a new message arrives on the server for you, but the server can't tell you. It has to wait for your browser to ask, "Hey, any new messages?" That's awful for real time. There's also the overhead problem where every single HTTP request carries headers, authentication tokens, cookies, and content types. These headers can be 500 bytes to 2 kilobytes. If you're sending tiny frequent updates like gamers, player positions, your headers might be 10 times larger than your actual data. And finally, it's half duplex. You can't send while you're receiving. It's like a walkie-talkie when one person talks, then waits, then other responds. We need full duplex, like a phone call where both can talk simultaneously. Before WebSockets existed, engineers had to get creative. They invented hacks to simulate real-time behavior on top of HTTP. Let me walk you through them. Short polling was the simplest approach. Every few seconds, the client asks the server any new data, and the server responds with either no or yes, and then repeat forever. The problem is that this is incredibly wasteful. If you poll every 2 seconds and there's like 3 updates per minute, 90% of those requests return nothing. You are just hammering your server and wasting the bandwidth. Long polling was smarter. The client asks for data instead of immediately responding with no. The server holds the connection open. It just waits and waits and waits. When the new data arrives or a timer occurs, then it responds back. Long polling reduces the latency because when the data arrives, the response goes out immediately. But here's the catch. Every single one of those held connection uses server memory. If you have 100,000 connected clients, that's 100,000 open connections eating RAM. Plus, you still have the header overhead on every request. We were clearly hitting the limits of what HTTP could really do. The web needed a new paradigm. And enter WebSockets. In 2011, the game changed. WebSockets was standardized in RFC 6555. And suddenly we had a true bidirectional, full duplex communication over a single TCP connection. What does it mean in plain English? It means that once you connect, the pipe stays open. The server can push data to you whenever it wants, and you can send the data to the server whenever you want, both at the same time in parallel. After the initial handshake, there are no more HTTP headers. You are sending tiny binary frames. A message that would be 1 kilobyte with HTTP might be 10 bytes with WebSockets. The overhead is minimal. WebSockets use WS for unencrypted connections, port 80, and WSS for encrypted connections over TLS, port 443. This is what powers every modern real-time app like Discord, Slack, Figma, collaborative Google Docs, multiplayer games, live dashboards, real-time trading platforms. If data updates frequently and latency matters, WebSockets is the answer. A WebSocket connection starts its life as a regular HTTP request. Then it upgrades to WebSocket protocol. Let me show you how this exactly works. The client sends a normal GET request but with some special headers. We have the GET request, we have the host, we have the upgrade, the connection, and the sec WebSocket key. The upgrade WebSocket header is essentially the client asking, "Hey, can we switch from HTTP to WebSocket?" The connection upgrade header confirms this intent. The sec WebSocket key is the random base64 encoded value that we will talk about in a moment. If the server supports WebSockets and accepts the upgrade, it responds with the status code 101. Switching protocols. 101 is special. It literally means I'm changing the protocol right now. After this response, the connection is no longer HTTP. The same TCP socket is now speaking the WebSocket protocol. No new connection needed. We just transformed what we already had. Now you might look at sec WebSocket key and think this must be for encryption. No, it's actually for handshake validation. Imagine there's a misconfigured HTTP proxy setting between you and your server. It doesn't understand WebSockets. If the client sends you an upgrade request and the proxy just passes through whatever response, things could break badly. The sec WebSocket key ensures that the server is actually a WebSocket server and that it understands the protocol. The client generates a random key, the server takes this key and appends a magic GUID. The server hashes this combined string with SHA-1 and base64 encodes the result, and the server sends this back as sec WebSocket accept. Your browser then does the same math locally. If the value doesn't match, the connection is immediately killed. This proves that the server understands WebSocket protocol and it isn't just some confused HTTP server echoing things back. It's not just encryption, it's protocol verification. Once the handshake is complete, we are not sending ASCII text anymore. We are sending binary frames. Every piece of data has a specific structure defined in RFC 6555. Let me break it down for you. Fin bit. This indicates if this is the final frame of a message. Why does this matter? Because large messages can be split into multiple frames. The fin bit tells you this is the last piece. You can assemble the full message now. Opcode. This is a 4-bit value that tells the receiver what kind of data this is. Is it text, binary, a control signal? We'll cover all these specific opcodes in next. Mask bit. This indicates if the payload is masked. All client to server frames must be masked. We'll explain why shortly. Payload length. How many bytes of data follow? Payload. The actual data you are sending. This frame structure is incredibly efficient. The minimum overhead is just 2 bytes for small frames. Compare that to the hundreds of bytes for HTTP headers. Let's talk about opcodes. They tell the receiver how to interpret incoming data frames. Opcode 0x1 or just 1 means text frame. This payload is UTF-8 encoded, text perfect for JSON. Opcode 0x2 means binary frame. This payload is raw bytes, great for images, videos, or any binary data. Control frames start with opcode 0x8 initiates a connection close. It's like a grateful goodbye that includes a status code. Opcode 0x9 is a ping, a heartbeat check. Opcode 0xa, that's 10 in decimal, is pong, the heartbeat response. These control frames maintain the connection health without mixing into your application data. The separation is clean and elegant. When you see opcode 1, you know immediately this is text. I can pass it as JSON. When you see opcode 8, you know the connection is closing. Clean up the resources. Here's a problem we do not anticipate. Your WebSocket is idle for a minute and it suddenly dies. What happens? Load balancers, firewalls, NAT routers, all of these network intermediaries have timeout policies. If they see a TCP connection sitting there doing nothing for 30 to 60 seconds, they think it's stale and kill it to free resources. WebSockets solve this with the built-in ping pong frames. Here's how it works. The server periodically sends a ping frame opcode 9 with some optional payload. The browser automatically responds with a pong frame opcode 10 echoing that payload. This tiny bit of traffic keeps the connection alive in the eyes of intermediaries. Most browsers handle the Pong responses automatically. You don't even have to write the code for it. But, and this is important for production systems, many developers also implement application level heartbeats. You might send a JSON message like type ping every 30 seconds. Why? Because browser's WebSocket API doesn't expose raw ping pong frames, so you can't easily detect if the server is actually processing or just the TCP is open. Application heartbeats give you that visibility. If you capture WebSocket traffic in Wireshark, you will notice something odd. Client to server frames look like garbage, but server to client frames are readable. That's masking at work. The rule is simple. All frames from client to server must be masked. Frames from server to client are not masked. But why? It's not for encryption. The data is trivially unmasked. It's to prevent something called cache poisoning attacks. Let me explain the vulnerability. Imagine a malicious JavaScript on a web page. It opens a WebSocket and carefully crafts bytes that, when passing through a transparent HTTP proxy, looks like a valid HTTP response. The proxy, confused, might catch this fake response. Now, legitimate users are asking for that URL get poisoned content. Masking defeats this because the attacker can't predict what the final bytes will look like on the wire. The 4-byte masking key XORs with the payload in a way that it scrambles any attempt to craft a specific byte sequence. It's a defense against man-in-the-middle proxies that don't understand WebSocket protocol. Using WebSockets in browser is surprisingly easy. The API is beautifully simple and event-driven. First, you create a connection, then you attach the event handlers like socket on open, socket on message, on close, and on error. You can send strings or binary data, and this event driven model is incredibly powerful. Instead of asking, do you have new data in a loop, you just call this function whenever data arrives. It's reactive, it's efficient, and it's the pattern used by every real-time application. On the server side, things are a bit different. First, you will use a library like WSPackage, which is lightweight, or Socket.io, which is a feature-rich, and automatic reconnections and fallbacks. The crucial difference from HTTP is that in HTTP, you handle a request and send a response. Done. With WebSockets, you store the connection and keep it alive. Typically, you maintain a set or a map of active connections. You add connections when they arrive, remove them when they close, and broadcast messages to everyone else. This is the foundation of any chat room or real time collaboration tool. The key insight is that you're managing the state now. Every client is a living object in memory, not just a request. Scaling WebSockets is hard, much harder than scaling HTTP. With HTTP, it's easy. You put a load balancer in front of 10 servers. Request 1 goes to server A, request 2 goes to server B. Who cares? They are stateless. Each request is independent. But WebSockets are stateful. The socket connection lives in one specific server's memory. Client A is connected to server 1, client B is connected to server 2. Now, the issue is client A sends a message meant for client B. Server 1 receives it. Server 1 loops through its client and the client B isn't there. Client B is on server 2. Server 1 has no idea client B even exists. The fundamental challenge is horizontal scaling breaks communication between clients on different servers. You can't just add more servers like you would with HTTP. You would need a way for servers to communicate with each other. The connections are isolated islands and we need to build bridges. This is where architectures get interesting, and many teams underestimate this complexity until it's already in production. The standard solution to the scaling issue is publish subscribe pattern, commonly implemented with Redis as a message broker or backplane. The architecture is as follows. Client A connected to server 1 sends a chat message. Server 1 receives the message. The server 1 publishes the message to a Redis channel like chatroom 123. Server 2, server 3, server 4 all subscribe to that channel. Redis instantly broadcasts the messages to all the subscribers. Each server receives the message and pushes it to their local WebSocket clients. Redis acts as the central nervous system. No server needs to know about clients or other servers. They just need to listen to Redis. Redis is perfect for this because it is in memory, so it is incredibly fast. PubSub is its first class feature, and it is proven at massive scale. This pattern extends beyond chat, real time dashboards, collaborative editing, live notifications. Anytime you need to broadcast state changes across a distributed system, PubSub is your friend. The trade off, Redis becomes a single point of failure. In production, you want a Redis cluster or a Redis Sentinel for high availability. Let's talk about putting a load balancer in front of WebSocket servers. There are some gotchas you need to know. Sticky sessions. If you're using a library like Socket.io that starts with HTTP long polling before upgrading to WebSocket, you need sticky sessions or session affinity. This means that load balancer ensures all requests from the same client go to the same server. Why? Because the upgrade handshake must complete on the same server that started the polling session. Connection timeouts. Load balancers like Nginx or HAProxy have timeout sessions for HTTP connections, often 60 seconds. But WebSocket connections need to stay open for hours. You must configure longer timeouts. Without this, your load balancer will cut connections thinking they have stalled. Layer 4 and Layer 7. You can either terminate TLS at load balancer layer 7 or forward plain WebSocket or pass through encrypted traffic directly layer 4. Each has trade-offs in terms of certificate management and inspection capabilities. Test your load balancer thoroughly and always use WSS in production. Always and no exceptions. WSS is WebSocket secure, WebSocket over TLS running on port 443. It's non-negotiable because first it gives you security. Without encryption, anyone on the network can read your WebSocket messages, chat, game moves, financial data will all be exposed. Firewall pass-through. Many corporate firewalls and ISPs block non-standard traffic on port 80. HTTP and WebSocket frames don't look like HTTP, but on port 443 traffic is encrypted. The firewall can't inspect it, so it lets pass through. WSS significantly improves the connection success rate in restrictive networks. And browser enforcement. If your web page is served over HTTPS, which it should be, modern browsers block unencrypted WebSocket WS connections. It's called mixed content blocking. You'll get this error in console and the connection will fail. The certificate for WSS is the same one you use for HTTPS. If you're already set up with HTTPS via Let's Encrypt or something similar, WSS works automatically on that same domain. Let's wrap up by looking at the future. HTTP 2 and WebSockets. In HTTP 1.1, when you upgrade to WebSocket, you take over the entire TCP connection. But HTTP 2 introduced multiplexing multiple streams over one connection. RFC 8441 defines how to bootstrap a WebSocket connection inside a single HTTP2 stream, allowing other HTTP2 requests to share the same connection. More efficient use of resources. HTTP3 and Quick. HTTP3 runs over Quick, which uses UDP instead of TCP. And why does this matter? Because TCP has head of line blocking. If one of the packet is lost, everything behind it waits. On unreliable networks, this causes stuttering. Quick eliminates this by handling streams independently, perfect for real-time communication. And web transport. This is the exciting future. Web transport is built on HTTP3 and provides both reliable streaming and unreliable datagram delivery. For gaming or video where some data loss is acceptable, unreliable delivery means lower latency. It's like having WebSockets and UDP datagrams in one API. The web platform keeps evolving. WebSockets was revolutionary in 2011, and new protocols are extending that revolution. If you're building the next generation, keep an eye on these protocols. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.